Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on Java Native Interface JNI, and we looked at the overloading and overriding behaviors of JNI, and we said that for overloading specifically, there is a strict rule that JNI follows. And we already looked at a few different cases where we overload a native method with a non-native method or a native method with another native method. And we said that in overloading, the only thing that is important is the name of the method and the parameter signature. And that's why in order for JNI to create a unique signature for these different methods, it has to use this underscore and then method parameter signature. And so far we have looked at the parameters that are double and then parameters that are objects, for example, and we said that objects are specified by L and the full path or fully qualified name of the class and then semicolon. All right, and then we said that arrays, one-dimensional arrays, are specified by square bracket D, square bracket, and then the type here it's double, so it becomes a square bracket D double. But then we said that with JNI doesn't use the square bracket. We cannot have a square bracket in the method in the function name, so instead a square bracket gets translated to _3. And we said that semicolon gets translated into _2, and then if we have a slash, it gets translated to underscore. All right. And then, but there are also other types that basically JNI uses, and here's a table. I thought this is a very good place to look at all these primitive types. So there are two things. One is the types that are going from Java to the native type and coming back. The boolean becomes JBoolean, byte becomes JByte, char becomes JChar, double becomes JDouble, float becomes JFloat, int becomes JInt, long becomes JLong, short becomes JShort, and void is void, right? Because void is just nothing. And these are typically used for return type of the functions or basically the variable types. All right, and then these types, obviously we have a JNI that defines, for example, JDouble, JFloat, but then we also have a JNI underscore MD or machine dependent, right? And the machine dependent guarantees that basically it defines the JInt and JLong or JShort or JByte, for example, such that they always adhere to the Java specification, which means that JInt, regardless of the platform, it always ends up being 32-bit signed. JLong ends up being a 64-bit signed, and then for example JByte ends up being a 8 bits signed. And because a character or a char in C++ is 1 byte, so if you just use a signed char, it's 8 bits that is signed. And so if you look at your JNI underscore machine dependent MD, you see that JByte is most likely is defined by a signed char. All right. But then for these overloading types, we also need to know the signature of these types. Like, what is the signature of double? We already saw that it's a capital D. What is the signature, for example, of a boolean? It's Z. What is the signature of byte? B. What is the signature of char? C. What is the signature of double, which we already saw, is D. What is the signature of float? F. What is the signature of int? I. What is the signature of long? It's J. So it's not capital L, right? Because capital L is already a long notation in C++, so we cannot use capital L. All right. Short is S and void is V, right? And these are the signatures. And again, we said that objects are L, start with L, and then fully qualified name, semicolon, okay? An array of some type, for example, a double array or whatever is a square bracket, and the type is basically has this type of signature. And then a method signature in general is round brackets, the type of the arguments, and the return type, which we have already seen in these comments. These are very useful comments that the JNI creates for us. So the signature of the method is round brackets, and the parameter signature, which is a square bracket D, which means this method takes an array of double values. All right. and then returns a square bracket D or array of double, right? So that's the signature of the method. Now in order to see these in action, let's head to Eclipse, and this is our native and native C, and then let's create a new package, for example, test4, and here I'm just going to create a new class, test types, for example, and I want to have, for example, public static. I'm going to, let's say, return void. I don't want to return anything, or maybe let's say return boolean func1, and then let's say it takes a boolean param. All right, so obviously we want this to be public native. I want to be a native, and then I create another one, public and native, let's say void func2. So I'm not using the same name because I want to avoid overloading for now, and let's say it takes it doesn't take anything. All right, but in order to see the void signature, I overload this func2 with, let's say, a short param. So we have one function, two functions that are overloaded, and then what are the other types here? Short, let's say long. Let's try long. So public native void func3, it takes a long, let's say, param. And then we can try another thing, public native void func4. Now let's try an object, let's say double object, double param. So these two are overloaded. Here I'm trying to look at the boolean types. Now the return type, so what do we expect here? So the return type of the C++ function is JBoolean, and then the parameter signature is again JBoolean. All right, but then if I want to see where these basically these signatures for the types are being used, then I have to, let's say, for example, overload this. So func1 boolean, let's say double x, and then it has to add the description. So to recap, the way we write the description of the overloaded is basically Java underscore package name, test4 underscore class name, test types underscore method name, func1 underscore underscore to signify overload, and boolean, it becomes z, right? Z is boolean. And then for the second one, signature of the overload is z and then d. Okay, and then the return type is boolean. Here the parameter is boolean, and then we have another one which is j double. Okay, so let's look at this. So what I'm going to do, I'm going to create my use Java H tool, and Java H is already configured to put the output or the generated I'm using this -d, which means -directory, and you give it a directory to put the generated header files. And I'm saying that take the path to workspace location, basically the root, and then native C project, and then header. Note that if you use, when you're using forward slash from the workspace, you have to use the semicolon. Okay, so workspace semicolon, and then a slash the project, a slash the folder inside the project. So this way I'm just directly creating the header file and putting it in this header folder in my native method. Okay, so if I run Java H, it's compiling one of my C projects, and then I should get the test types, for example, here. Let's refresh. Let's run it one more time. Say it does not. Okay, so I have to, basically you have to select the class, right? And then run the Java H. Now we should be able to get the test underscore test overload. Again, the naming convention here is that the package underscore class name. So this is the Java C, basically Java H. or the header file generated by the Java H. And as you see, we have two overloaded functions here that correspond to the func method. All right. And then oh, sorry, this is the wrong one. We need to have test types. All right, test types. So we have func1, and then as you can see, underscore signifies the overloading, and then boolean is basically translates into boolean has a signature parameter of z. All right. So underscore z means this is an overloaded method which takes a parameter of boolean type and then returns a jboolean, which again has a z. And the parameter type was boolean, which gets translated into jboolean. And if I open this type definition, it's in the JNI H. And as you can see, jboolean Java specification has a boolean of 1 byte, right? And we know that char in C++ is 1 byte. So we just define the jboolean as an unsigned char. All right. And then short is 2 bytes, and we know that char is 2 bytes basically in Java because it uses UTF encoding. And then so short is 2 bytes. Unsigned short means a positive 2 byte integer. So we have this header file, and then void. So for, as you can see, the return type is void, but when we had this basically this function doesn't take anything, but we are overloading this. So we were expecting to see something like v, but there is no point in writing v, right? So it just writes underscore but doesn't write anything. So means this method is overloaded, but it doesn't take any parameters. So the parameters are void, and the return type is void, and the void is the same for Java and C++. Okay. And so back to our PowerPoint, instead of v, we can also say, for example, nothing. Basically, we don't need to write anything for the void type. And then we have another func that is overloaded by a short. So this is func2. So if I take func2, short is basically, I'm expecting to see an s here. So s is short, and again the return type has a signature of void. And then the short in Java translates into JShort type. And if you look at the definition of this JShort, is just the short, because the short is a signed short. So short in Java is 2 bytes signed integer. Short in C++ is also 2 bytes signed. Char is 2 bytes in Java, but it's unsigned integer, so we use an unsigned here. Okay. Now obviously double and float are basically the same. Short is the same. Int is not the same. So if you look at jint in the machine dependent, so the reason it's in jint and jlong and jbyte are in the machine dependent header file, JNI header file, because Java has to guarantee that jint always ends up being 32-bit signed, jlong always ends up to be 64-bit signed, and jbyte is 1 byte signed. And again, char is 1 byte. Signed char means it's a 1 byte signed integer, which is byte, the definition of byte in Java. So obviously for long, it checks the platform to see if it's a 32-bit or 64-bit. If it's a 32-bit, then jlong maps to long, and jint maps to long-int, right, on a 32-bit machine. But on a 64-bit machine, int is already 32-bit and long is already 64-bit. Okay. And then func3 takes a long, so this maps to jlong, and func4 takes a double object. So what do we expect to see here? For a double object, we expect to see a double. So what is the signature of double? If I go back to my Java perspective and then to the bytecode signature and click on this function, so the signature of this method is basically func l java lang double semicolon, and it returns void. So if I copy this description and go back here and paste it, so l so a slash becomes underscore, semicolon becomes underscore 2. So we expect a signature like this for this overloaded function func4. And so func4 was not overloaded, so maybe let's overload it with something else. Func4, let's say boolean or char c, and then we have another overloaded. Okay, so if I run my Java H again, let's go back to the C perspective. Java H again, I have to click on the type Java H and then test types, and now we have this func4 overloaded with underscore underscore. So for the first one, we have a character, and the character signature is C, so this becomes C for character, and then L Java underscore lang underscore double underscore 2 for the double object. So let's see. So C is character, and then L Java lang double underscore 2, and it takes a J char and J object. Note that we don't have a J capital double. Double is a Java object, so the parameter type is J char and J object. And we will, in the future lectures, I discuss how to actually work with these J objects and call the methods inside these classes. So this is our header file, and I hope this is very clear. And then the other thing here is that if you want to know why Java uses these for these overloading signatures, it's because in the JNI, these types are defined exactly the way Java is using them. So you cannot use anything else but Z. If you use that, then Java doesn't know what to do with it. So if you look at the JNI header file and then search for J value, you see that all these types are defined. So Z is defined as J boolean, B is J byte, C is J char, S is J short, I is J int, J is J long, F is J float, D is J double, L is for object, so it's a J object. And maybe also let's look at the signature of a long. So I'm going to overload func3 with the X value, with a double value, and then create the header file again, select my Java file, and then run the Java H on this, and then test types. And now we have this func3 which is overloaded. And again, long gets translated into capital J. So what we expect to see here as a signature for this overloaded method for func3 is capital J. And for the other one, func3, capital J is first param, capital D is a double, the second parameter. And we see that underscore underscore J. So J means long, and JD means long and a double. And the return type is void, V. Okay. But again, if the parameter type is void, it's not taking any parameter, then we don't write anything, right? We just write underscore underscore. So the question is, does Java allow to actually write void as a parameter type? And the answer is no. So you cannot write something like this. It's a error, right? Java doesn't allow you. But in C++, you can do that because you can pass a void pointer to the function parameters. But in Java, you don't have pointers, so you cannot use any void parameter. You cannot have a type parameter of type void. It's not allowed in Java. Okay. So the next topic here is working with primitive arrays. So far we have worked with primitive types. So we have written functions that return double, and then and the double is D. Basically it returns a J double. If it's float, it returns J float. So working with primitive types is very easy. So if the function returns a boolean, the C++ signature returns a J boolean, J byte, J char, and these are all primitive C++ types, J boolean, J byte, J char. So there is no real conversion here. But if we want to work with primitive arrays, we have to be careful, because the primitive array in Java and the primitive array in C++ are completely different. So I cannot create a primitive array in C++ and return it as the return parameter of a function to Java. It doesn't work like that. So we have to use some sort of conversion here. And this is where that JNI environment pointer comes into play. So the good news is that this JNI environment pointer takes care of everything, all these conversions that we need. So primitive types, we can directly return them from a Java, a C++ function to a Java class, and I'm going to demonstrate it. So I'm going to create another class called test primitive, and then here I'm going to have public native boolean is odd, and then int x. Okay, and then what I'm going to do, I'm going to select it, test primitive, and then run java-h to create the header file, and it should appear in my header file in the C++ project, test primitive. So this has only one function, java underscore package name underscore class name underscore method name, and the signature is integer, which is jint, and it returns a boolean or jboolean, and the jboolean maps to unsigned char. So jboolean doesn't map to the bool primitive type of the C++. Just be very careful about it, right? Because the bool in C++ and boolean in Java, they don't match, the types don't match. So what do we do here? So this JNI environment pointing is not necessary. To use JObject, let's call this test primitive. That's our object. This is a reference to this object because this is not static, so we can instantiate it. And then jint is just x, right? And then the return type is jboolean. So let's try bool first. Bool basically result is x mod 2. I'm using the ternary operator, and then if x mod 2 I return false, else I return true. And then I want to try to return the result. Okay. Okay, so this is in the header, so we shouldn't do this in the header file. Maybe let me generate the header file again, java-h, and then I'm going to so test primitive, this is our header file, and I'm going to create a source cpp file, which is a compilation unit. Let's call this primitives.cpp, and finish. So what I'm going to do first is to include this header file using a relative path, header, and then test primitive, test primitive. And then I'm going to copy and paste the method signature, and then do the implementation here. JObject is test primitive, and then jint is x, and then I want to try bool, basically result is equal to x mod 2, false, it's not odd, and then true. And then I want to try to return result. Okay, now it gives me error because it says that symbol so syntax error. So why is this syntax error? So I have to put the question mark here and then the colon here. Okay, so it appears that everything works fine and it can return the bool. So let's try to compile this. I'm compiling in the debug mode, and native C dilib was generated, so apparently there was no problem. So we can try the Java one, paste. Sorry, I shouldn't put this here. I should put this in the lib native C, paste it in the Java project, and then I'm going into the Java project, and then I'm going to my class. Maybe let's try to create a main method, and then try to instantiate this class, test primitive test, new test primitive, and then sysout test.isOdd 5. So let's see the result. And then now it okay, so we need to load the library into memory, system.load library, and then the signature is native underscore C. Okay, so let's run it again, and it returns false. So what matters here is that we use the bool, and then the result was fine, but the JBoolean type is not exactly the bool type. It's the unsigned char type. Okay, on different machines this might be different, but this is defined in the JNI.h, so on different machines this probably remains the same. And then but we could also assign this to a basically unsigned char. So let's try to see if we can do that. But the point here is that you can directly return bool as a JBoolean. It works fine because the value is the same. But if we use the JBoolean, we can still do that, considering that the return type of this ternary operator is return true and false, but we're returning a JBoolean. Okay, so let's see if we can compile this, going back to our C++ perspective, and then compile this project, and then libnative C was created, and then copy and paste it again into our Java project, and then running our main method again, and it's still working fine. So if we use 8 for example, true. So my suggestion here is that always use the Java JNI defined types instead of the basically the C++ type. So I could use bool, and I could also use JBoolean, and I always prefer to use JBoolean because I'm 100% sure that these types match. All right, so for example, you can use double x is 2.1 and then return it, but I always prefer to use JDouble instead of double because I'm perfectly sure that then this works fine. Okay, and there is no problem with this. So always use the JNI defined types. So I'm going to write this here. Always use or it's a good practice to always use JNI defined types. So I can have another function, public native double func1 and double x, and by now you already know the routine. We select this, create or update the header file, test primitive, and then this is also added now, and then we go to our CPP and try to add the implementation. And JN environment, the J object, these are the same, and then J double X. So obviously there are two ways. So I'm returning a J double. Let's say I can define a double Y is 2 times X and then return Y. So I'm directly returning a JNI here. I'm directly returning a C++ type as a double, and it gets converted to J double. And we already know that double and J double are basically the same. J double on my machine is a redefinition of type double. All right, but this might not be safe exactly, especially for int and basically the types that are defined in the machine dependent header file JNI_MD for JInt, JLong, and JByte. So my recommendation is always to so let me compile this and show you that this works fine. So compiled fine, and then copy and paste to our Java project, and then here sysout test.func1 2.2, and it works fine, right? We're just taking the number and doubling it. But my recommendation is always to, instead of using the raw C++ primitive types, use the JNI defined types. So instead of double, I use J double. Y is 2 times X, and then return Y. Return Y. So here I'm confident that this J double matches exactly what the return type, and Java has no problem. So there is no problem with the conversion of the types. And I can copy this library, paste it into my Java. load it into the memory, and then you see this one also works fine. Okay, and we can also try one more, public native double or float, and then func2, and it takes a short or byte x. Okay, and then select the Java file, run the Java H tool, and it updates the primitive header file, and then copy and paste in our C++ file, which is our compilation unit. So byte is B, and then float is F, so we're returning a J float, and we're taking a J byte. And again, the environment pointer, the J object, which is a reference to the current object, and J byte X. And I already know that the J float maps directly to my float. Okay, so if I open this up, it maps to float. So I can return a float primitive type from C++ or return JFloat, and I always prefer to use JNI defined types, JFloat y equals. So what is this J byte? J byte is sign char J byte, right? So this is not exactly the byte in C++. So let's say take x plus 1.1 and then multiply it by 0.22. Okay, and then return y. And this is a byte and this is float or double. So the compiler is already doing some conversion here, but the result will be double. So the question is, does the compiler allow us to do this? The answer is yes. So the compiler allows us to use a float and assign a double to a float. Although there is a conversion or narrowing conversion happens here. So let's copy and paste this, and then sysout test.func2 that takes a byte 3. Okay, so the method func in type is not applicable for argument int, so we have to specify b or byte. Actually capital B, or maybe cast it directly to byte. And 0.902. So the C++ compiler was fine with us using doubles with a byte or unsigned char, and then assigning it directly to the float. Java typically doesn't allow this by default because there's some narrowing conversion happens, and Java want to make sure that we know what we're doing, so we tell it to explicitly cast it. Now obviously for numbers such as float we use F or F. For long we use L or L. For double is D or D. And then but for byte I guess we just explicitly cast it to a byte. Okay, so I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.